Have you ever really stopped to think about how this all works? I mean, how a machine that's basically just a bunch of switches can understand our world. From the letters on this screen to the sound of my voice, it all has to be translated into a language that computers can actually speak.
So, let's get right into the central puzzle. A computer, at its very core, only knows two things, on or off. We call that a 1 or a 0. That's it. So how on earth do you get from that super simple system to, all the different colors in a photo or the complex sounds in a song?
Well, the answer is something called binary code. This is the language of literally every digital device we use. By arranging these ones and zeros in really specific patterns, we can make them mean, well, anything. It's kind of like how the letters CAT aren't just letters, they represent the idea of a cat. In the same way, a binary string like 0101 can represent the number 5. Everything, and I mean everything, is just a super long string of these ones and zeros. The real magic is in how we decide to organize them.
Okay, so let's start with the basics. Text. To get a computer to understand letters, numbers, and symbols, the pioneers who built these things needed to create a kind of universal dictionary that every single machine could use. And that dictionary is called ASCII. It was created way back in 1963, and the idea behind it is just brilliant in its simplicity. It just assigns a unique number to every character you can type on a keyboard. So when you hit the A key, your computer doesn't see an A, it sees the number 65.
And here it is. This is that dictionary we were talking about, the ASCII table. You can look it up yourself. See, there's uppercase A, and yep, its code is 65. B is 66, C is 67, and it just keeps going. Even the spacebar has its own number. It's 32. This simple little chart is the foundation of pretty much all digital text.
And this is where you can see just how elegant this system is. The computer takes that number, 65, and stores it in binary. For an uppercase A, that's 01000001. Now look at the lowercase a. It's almost identical, 01100001. Did you catch the difference? Just one single bit flipped from a 0 to a 1. That tiny change is all it takes. It's incredibly efficient.
Now the original ASCII was great, but it was a little limited, so they added one more bit, going from a 7-bit system to an 8-bit one. And that one extra bit doubled the number of possible characters. This gave us extended ASCII, which made room for all sorts of things like accented letters and other symbols you need for languages besides English.
All right, so text is easy enough. It's just a lookup table of numbers. But what about something that isn't so neat and tidy? What about something like a sound wave? It's not like you can just assign a number to it. You have to figure out how to capture something that's totally invisible and always changing.
So sound moves through the air as waves. These waves have a frequency, which is what we hear as pitch, and an amplitude, which we hear as loudness or volume. A high-pitched sound has its waves packed really close together, while a loud sound has really tall waves. So for a computer to digitize sound, it has to find a way to measure these two things. The thing is, a computer can't store a perfectly smooth, continuous wave. It just can't. So instead, it takes a whole series of tiny little snapshots. This process is called sampling. Think of it like a strobe light flashing on that sound wave. Every single flash captures the wave's height, its amplitude, at that one specific moment in time. And this graph shows you exactly how that works. At the first interval, the computer measures the wave's height and stores a number. Let's say it's 10. A split second later, it measures again and gets a 4, then a 1, and it just keeps doing this over and over. The digital audio file you end up with is really just the huge list of these numbers that tells the computer how to redraw the wave. So the key factor here, the thing that really matters, is how many of those snapshots you take. That's what we call the sampling rate. The more samples you grab every second, the more detailed and accurate your digital version will be. A really low rate can sound all choppy, but a high rate sounds smooth and just like the real thing. And when I say a high rate, I'm not kidding. To get the audio quality you hear on a regular CD, the machine is taking 44,100 samples every single second. Think about that. 44,000 measurements just to capture 1 second of music. It's incredible. So, we've covered text and sound. Now for the last big piece of the puzzle, visuals. How does a computer take a photograph with all its detail and millions of colors and turn it into numbers? Well, the approach is actually a lot like how it captures sound. It all comes down to one thing, the pixel. Pixel is short for picture element, and it's the tiniest possible dot of color that a screen can show.
Every digital image you have ever seen is nothing more than a giant grid, like a huge mosaic made of thousands or even millions of these little colored squares. So how does a computer know what color to make each of those little squares? You guessed it, with bits. We call this color depth. If you only use 1 bit for each pixel, you can only have 2 colors, like black and white. But if you use 8 bits, suddenly you can have 256 different colors. And most modern computers use 24 bits for every pixel, which gives us, wait for it, 16.7 million possible colors for each and every one of those tiny dots. And the other part of the story, of course, is resolution. That's really just the total number of pixels you're working with. So an image with a resolution of, say, 4,096 pixels wide by 3072 pixels high has almost 12.6 million individual pixels. That's 12.6 million little color instructions the computer has to remember.
And this picture just makes it so obvious why resolution is a big deal. Look at image A on the left. It's packed with pixels, right? It looks super sharp and clear. But as you move over toward E, you're losing pixels. The computer has less and less information to work with, so the image gets all blocky and blurry, or pixelated, as we say. It's simple. More pixels means more detail. So whether we're talking about text or sound or images, you might be starting to see a common thread here. It seems like every time we try to get a more perfect, more accurate digital copy of something, we smash right into one fundamental, unavoidable trade-off.
Let's just go back to sound for a second. The benefits of taking more samples are obvious, right? You get much better sound quality, way less distortion. But there's always a price to pay. More samples means a much larger file, and it takes a lot more horsepower from your computer to actually play it back. And this is the great digital balancing act. It applies to everything. Higher quality always comes at a cost. If you want sharper images, it's going to cost you more storage space. If you want richer sound, it's going to cost you slower download speeds. We are in a constant battle, trading perfection for convenience.
You know, a quote from our source material really just hits the nail on the head. It says, "The main drawback of using high-resolution images is the increase in file size. You can have the most stunningly beautiful image in the world, but if the file is so massive you can't email it or load it on a website, what's the point?" This is the struggle that engineers and artists and all of us deal with every day.
So, I guess that brings us to one last thought. When you're listening to music, do you stream at the highest possible quality, even if it eats up your data plan? When you take a photo, do you save the giant full-resolution file, knowing it's going to fill up your phone? It really makes you think. When it's quality versus convenience, which one wins for you?